What is the specific problem that the proposed method aims to solve in the paper?
The specific problem that the proposed method aims to solve in the paper is to improve the reasoning ability of language models, particularly in chain of thought, COT reasoning tasks. The paper introduces an approach called Iterative Reasoning Preference Optimization, Iterative RPO, that utilizes iterative preference optimization to enhance the performance of language models on reasoning tasks. The method focuses on generating multiple chain of thought reasoning steps and final answers for training prompts, constructing preference pairs where winners have correct answers and losers have wrong answers, and then training a variant of DPO that includes a negative log likelihood NLL loss term for the pair winners. By iterating this process and updating the model with new preference data, the proposed method aims to improve reasoning performance over multiple iterations until it saturates. The goal is to outperform baselines such as supervised fine-tuning, SFT, and standard DPO, ultimately enhancing the reasoning ability of language models across a variety of tasks.
How does the proposed method work, and can you illustrate it step by step?
The proposed method, Iterative Reasoning Preference Optimization, Iterative RPO, works by iteratively training a language model on reasoning tasks, specifically focusing on chain of thought, COT reasoning. The process involves two main steps on each iteration: chain of thought and answer generation and preference optimization. 1. Chain of thought and answer generation. Given the current model M_T, the model generates multiple responses for each input, consisting of COT reasoning steps followed by a final answer. These responses are then evaluated based on the correctness of their final answers, compared to the gold labels provided in the training dataset. 2. Preference optimization. The generated responses are then used to construct preference pairs, where winners have higher rewards correct answers than losers. These pairs are used to train a new model M_T+1 by combining the DPO loss for learning from the preference pairs and the negative log likelihood NLL loss for learning over the winning responses. The loss function is optimized for each preference pair to update the model parameters. This iterative process continues over multiple iterations, with each new model being trained using preference data created by the previous model. The training data is constructed from the generated responses and preference pairs, leading to improved reasoning performance over each iteration until it eventually saturates. The method outperforms baselines like zero-shot COT, supervised fine-tuning, SFT, and standard DPO, showcasing significant improvements in reasoning ability across tasks like GSM-8K, ARC Challenge, and Math.
What are the theoretical or practical benefits of using this method according to the paper?
The theoretical and practical benefits of using the Iterative Reasoning Preference Optimization, Iterative RPO, method outlined in the paper include significant performance improvements in reasoning tasks, such as chain of thought, COT reasoning. The method leverages iterative preference optimization to train generative reasoning models, leading to enhanced reasoning ability of large language models, LLMs, across a wide range of tasks. The approach allows for the construction of preference pairs where winners have correct answers and losers have wrong answers, facilitating effective model training. By incorporating a negative log likelihood NLL loss term for the pair winners, the method ensures crucial performance enhancements. Additionally, the iterative nature of the approach, where new pairs are generated and the model is trained again from the previously trained model, results in continuous reasoning performance improvements until saturation is reached. The paper demonstrates that iterative RPO outperforms various baselines, including supervised fine-tuning, SFT, and standard DPO, showcasing its effectiveness in enhancing reasoning capabilities. Overall, the method provides a simple yet powerful recipe for improving reasoning ability in LLMs, offering a promising approach for optimizing model performance in reasoning tasks.
How were the results achieved with the new method presented in the paper?
The results were achieved with the new method presented in the paper, Iterative Reasoning Preference Optimization, Iterative RPO, by iteratively applying preference optimization to reasoning tasks, specifically focusing on chain of thought COT reasoning. The method involves two main steps on each iteration: chain of thought and answer generation and preference optimization. In the chain of thought and answer generation step, the current model generates multiple responses for each input, consisting of COT reasoning steps followed by a final answer. The correctness of the final answer is compared to the gold labels provided in the training dataset to derive rewards. In the preference optimization step, a dataset of response pairs is constructed based on the generated responses, where winners, responses with higher rewards, are paired with losers, responses with lower rewards. A new model is then trained using a loss function that combines the DPO loss for learning from the preference pairs and the negative log likelihood NLL loss for learning over the winning responses. This iterative training process leads to improved reasoning performance over multiple iterations until it eventually saturates, outperforming baselines such as supervised fine-tuning (SFT) and standard DPO. The method was tested on tasks like math word problems, GSM-8K, ARC challenge, and math, showing significant performance gains across iterations and outperforming other methods in the literature.
What are the limitations or drawbacks of the proposed method as discussed in the paper?
The limitations or drawbacks of the proposed method, as discussed in the paper, include the necessity of having a fixed set of prompts for each iteration, which may limit the model's ability to explore a wider range of inputs. Additionally, the method relies on the correctness of the final answers provided in the training dataset, which may introduce noise if the generated COT and final answers happen to be correct by chance, especially in tasks with limited answer choices like multiple-choice questions. Another limitation is the potential decay in performance gains across iterations, indicating an upper limit on learning, especially when iterating over a fixed number of prompts from the training samples. Furthermore, the method requires a significant amount of training data, as seen in the decrease in the number of examples in later iterations due to the lack of incorrect samples for some questions. Lastly, the method's reliance on preference optimization using DPO may not always lead to significant improvements on reasoning tasks, compared to other training methods that focus on finding high-quality samples for supervised fine-tuning.
What future work do the authors suggest based on the findings in the paper?
Based on the findings in the paper, the authors suggest future work that could explore the potential of combining iterative reinforcement learning from human feedback, RLHF, with preference optimization methods. Specifically, they propose investigating the integration of human-in-the-loop feedback to provide additional labels for retraining the reward model at each iteration, similar to proximal policy optimization, PPO, approaches. This could potentially lead to further improvements in performance across iterations. Additionally, the authors hint at the possibility of exploring novel iterative alignment methods that do not require human intervention, building on the success of iterative DPO and other similar frameworks. By continuing to refine and innovate on these iterative training techniques, the authors believe there is room for significant advancements in enhancing reasoning abilities of language models across a variety of tasks.